We get vapor pressure data in one of two ways. For pure water, the amount of vapor right above it is really a property of that fluid, in this case water, and that is the vapor pressure. So this data, the vapor pressure data, is available for water in many places, including our textbook. And then as you increase the temperature, as you go this way, then it is easier for the water molecules, because they have more energy, it is easier for them to get into the vapor phase. So you're going to have more vapor there. So the vapor pressure increases. The vapor pressure increases until at 100 degrees it is equal to 1 atmosphere. So you have only vapor here. For a hygroscopic solid, for a hygroscopic material such as a skin, then the amount of vapor right above the solid is going to depend on how much moisture is there in the solid. In fact, more or less moisture there is in the solid, there is going to be less vapor here, which makes sense. More moisture there is, more is going to be the vapor. So this information is provided as the moisture in air, which is like the amount of vapor in air, as a function of moisture in the skin. So for a given moisture in the skin, you can find how much is the moisture in the air. So this moisture in the air, the variable that is used in practice is water activity, which is vapor pressure divided by the vapor pressure of pure water. That's the part that we did here. So this is the vapor pressure of pure water. So from here we can find what is PV. Now, because on the surface the amount of vapor in the air and the amount of water in the solid, they are in equilibrium, we can also go this way. Given a value of water vapor on the surface or the water activity on the surface, we can find what is the moisture content in the solid right at the surface. So these are the two ways of getting vapor pressure for pure water and for any hygroscopic material, for which for that material you have to be given information like this, otherwise you cannot find it. We further elaborate the lower vapor pressure above a wet solid using the example of pure water and skin, human skin. And even though I have plotted the data for human skin, which is slightly lower, it's kind of hard to see. So I have expanded this region here, above. So at 35 degrees, see, we have data for pure water, and then we have data for human skin at two different moisture content. So you notice as you reduce the moisture content, the vapor pressure goes down. It's because the water is held more tightly by the solid, the skin in this case, and therefore not as much of the water can escape into the vapor. So vapor pressure is lowered with moisture content, and that's the information that I showed in the previous slide. Once we get the vapor pressure, from the vapor pressure we can find the vapor concentration using the ideal gas law this way. So if I write the ideal gas law, PV equals nRT, then concentration defined as moles per unit volume is equal to P over RT. So that's my concentration. So therefore, vapor concentration can be found from partial pressure of vapor that's read from either the table for pure water or from graphs of the kind that I showed earlier, and you can find the concentration of vapor in moles per meter cube. This is something we're going to need later on for solving transport problems.